Hello students, welcome back once again to our That's It YouTube channel. I'm KASU SIR discussing here the critical concepts of the organic chemistry, linking chapter by chapter. So what I try to ensure here that the proper connection between the chapters is being established and the questions which were asked previously in the JEE Advanced can be solved so easily, that means within a stipulated time or within less than 3 minutes of the period. So now I gave as much easy solutions as possible. Follow my last 9 sessions of the JEE advanced preparation videos, and in the coming 5-6 sessions we are going to learn the entire organic as well as inorganic chemistry. So stay tuned to my classes. Now let's pick up the first question of the day. You can see that the question is actually from the Dove's process. You have to calculate here the weight percentage of the hydrogen in a product which is obtained after a series of reactions. You can see that Dove's process is an intensive process where high temperature and pressure are being applied, so that through benzene mechanism, you know that this is called benzene mechanism, your chlorine can be replaced by the OH. This is called Dove's process, isn't it? Of preparation of phenols. So this comes in phenols, very important reaction, and that forms benzene as the reactive intermediate, isn't it? Now after that, you see you are treating this with the concentrated sulfuric acid, wherein your ortho para positions of the OH are substituted by the sulfonate groups. First sulfonation occurs on phenol when you are about to do the nitration, and subsequently this, when heated with the concentrated HNO3, not only SO3s will be eliminated but NO2 also substitute at ortho and para. So first sulfonation and then nitration is the concept of the nitration on phenol. So you will be getting 2,4,6 trinitrophenol, which is popularly known as the picric acid. Very acidic, isn't it, because of the NO2 groups. Now the question is to determine the weight percentage of hydrogen in Q. You can see how many hydrogens are present, isn't it? You can see that there is 1, 2 and 3 hydrogens are present in the compound. So 3 into mass of each hydrogen by total mass of the compound. When you write the formula of this compound, you can see that there are 6 carbon atoms, isn't it? There are 2 plus 2 plus 2 plus 1, that is 7 oxygens, alright, 3 nitrogens and 3 hydrogen. So you are determining the mass percentage, that is 3 into mass of hydrogen by total mass, that is equal to 6 into 12 plus 7 into 16 plus 3 into 14 plus 3 into hydrogen, that is equal to 1 into 100. So that's it. So this is the percentage of hydrogen that you have to find out of these compounds. So easy question, straight question. Only this part need to be focused. This is anyways the basics of electrophilic aromatic substitution that you will cover in your board exam also, isn't it? Let's see the next question. I want you to do the calculation part, right? You know, calculation is not my domain, right? You know, you have to do the calculation and find out how much answer you're getting. I'm not writing the answers here up front. If there is any multiple choice correct answer, then I'm giving you the options, right? If there is any numerical value based or any subjective kind of questions, I'm giving the solution, leaving the calculation part to you so that I can save the time. Now you can see you got this is sent to through the iron tube or copper tube, the very famous reaction of acetylene, where when it is sent through the iron or copper tube, very popular reaction where 3 moles of acetylene would combine with each other to give you what? Benzene. So 3 mole of the acetylene gives rise to benzene. Now this is again subjected to the Friedel-Crafts reaction, alright, Friedel-Crafts alkylation, where you will be getting a primary carbocation which is converted into secondary carbocation, giving rise to cumene or isopropyl benzene. So this is your product A. and this is your product B after the reaction with propyl chloride. You know that the very popular reaction related to the cumene is cumene hydroperoxide reaction. So what will happen here afterwards? This reacts with O2 to give you cumene hydroperoxide, CHP. What's that? OOH, and this subsequently undergoes rearrangement when treated with H plus to give you phenol, isn't it? So phenol is obtained, and this is heated with the acetyl chloride in presence of AlCl3 of pyridine, where your HCl will be lost to give you ultimately OCOCH3. Alright. So this is the final product that you have obtained. So different percentage yields. Alright. So you took how many mole here? 15 mole. You know, 3 mole giving rise to 1 mole. So for 15 mole I will be getting how much? 1/3 of 15, that is 5 mole of this. But you can see only 80% of the reaction is taking place. 80% of 5 means how many? 4 mole only I am getting. So you can see this is undergoing the Frelcraft alkylation to give you 50%. That means 4 moles should give rise to 4 moles. 1:1 is the mole ratio, isn't it? But you can see that 50%, that means you will be getting out of 4 moles only 2 moles. The mole ratio is remaining as 1:1. That's the advantage here. Now you can see out of that, again this is your B and you got C. Alright, so C is phenol and this is your D. So now we can see that these 2 moles of the substance, 50% of C is obtained. The 2 moles ka 50% is nothing but 1 mole of phenol is obtained, and this is giving rise to ultimately C is giving rise to D, but this product yield is 100%. That means this is 100%. So you will be getting what? 1 mole of the final product, and you have to find out what is that you have to find out? The amount of the product D, that is nothing but 1 mole, which is nothing but the 1 mole means molar mass, right? You can find out this molar mass is C. Molecular formula you write down C6 plus 2C8. Hydrogens are 5 plus 3, 8. Oxygens are 2. Alright, so 12 into 96 plus 8 plus 32. So this is the answer to this question. Easy question, isn't it? Next, let's see the next question. The reaction sequence that would lead to orthoxylene. You know orthoxylene, isn't it? 2 methyls kept at the adjacent position is called orthoxylene. Let's see one by one, right? You can see that when you are carrying out the reaction with NaNO2 and HCl at 0 degrees Celsius cold condition, you know you will be getting first. I am writing here directly the product N2 plus and Cl minus. Then you know Sandmeyer reaction where that will be replaced by the cyanide. So here what I am writing is Me and Cn, and this dibal H, you know, very important, diisobutyl aluminum hydride is going to convert the entire cyanide into what? CHO. Like you know that first it gives rise to COOH, then it reduces that COOH into CHO, and this is added the Wolff-Kishner reagent N2H4 in presence of a base gives rise to the oxygen will be completely reduced to give you orthoxylene. So this is correct, isn't it? Now let's see this reaction. You know, first you will be getting MgBr, isn't it? Grignard reagent, and carbon dioxide gives rise to what? COOH. I wrote the product upfront. Then COOH will be converted into COCl. Only this change is happening because you are treating it with SOCl2. You know the purpose of SOCl2 is to convert OH into Cl. Now this is being heated with this reagent. So what do you get next? I am writing it here, right? So you will get C double bond H. Rosenmund reduction, isn't it? Now when this is heated with zinc amalgam HCl, that is Clemmensen reducing agent, you will be getting orthoxylene. Perfect, isn't it? Next, let's see. So that means you got orthoxylene from this also. So you can see the addition of diborane anti-Marconic addition, where your this thing will be converted into OH, and you can see that PBr3 will replace the OH by the bromine, and the treatment with zinc HCl will replace this by hydrogen. So what's the product which is obtained in this reaction? I hope you are following, isn't it? Ethyl methyl benzene. Over here you just check what's happening. You have to carry out first the OS analysis. That means you will be writing reductive OS analysis product. Alright, so what do you get? C double bond OH, CH2, CHO. This one subjected to the reduction by using N2H4OH minus, that is Wolff-Kishner reducing agent. You know that your oxygens are reduced. So this is CH3 and this is CH2, CH3. So these two are giving rise to methyl ethyl benzene, hence that cannot be the right answer to the question, isn't it? So right answer is option A and option B, right? Let's see this. What do you now? Let's see the second question. Very beautifully crafted question. Like you can see that this is the carboxylic acid with the alpha hydrogen atom. When treated with bromine in presence of red phosphorus, what will happen here? When you are treating with bromine in red phosphorus, this is called Hell-Vollard Zelensky reaction, isn't it? All right. Hell-Vollard and Zelensky reaction, where the alpha hydrogen and along with that the OH will be replaced by the bromine. Now this is through your first reaction, and then H2O is added. You should know that the bromine remains intact and you will be getting COOH. So this is your P. Now you can see that P is treated with the potassium thalamide, isn't it? So when you have got the potassium thalamide, which is a strong nucleophile, is going to attack over here to give you a substituted product. What is that? C double bond O, C double bond O. Very important Gabriel thalamide reaction, isn't it? CH, CH3 and then COOH, which is subsequently you can see that hydrolyzed in the alkaline medium. So what will happen? We are going to add HOH here. So what is that product finally obtained? I am writing it over here. So you got phthalic acid and alanine, isn't it? COOH, NH2 and then CH3. You have to pick up the right option from the given choices, right? P can be reduced to a primary alcohol using sodium borohydride. You know, since this is carboxylic acid, reduction is not possible. So A is not correct. You know that carboxylic acids are reduced to primary alcohols by using lithium aluminum hydride. Treating P with concentrated ammonium hydroxide followed by acidification gives rise to Q. You can see that this is Q. When I am heating this with ammonium hydroxide or ammonia, you know that HBr can be eliminated and gives rise to ultimately, right, amino acid, the Strecker synthesis, isn't it? Treating Q with a solution of NaNO2 and HCl gives rise to N2. Where is Q? No, this is Q. This is a primary amine. When primary amines are treated with the HNO2, you know that N2 is obtained. You have studied this in the properties of amines. P is more acidic than CH3, CH2, COOH. You can see that this is P and bromine group shows minus A effect and acidic strength increases. So this is also correct. So the right answer for this question is option B, C and D. You can see which of the following reaction leads to the formation of 1,3,5 trimethyl benzene. Let's see the reaction that we know already, isn't it, right? You know, option A. What happens here? You have got the aldol condensation reaction, CH2, H, alright, single bond, C double bond O, CH3, CH2, H, C double bond CH3. So in option A, you can see that I am eliminating H2O. Alright, so I am eliminating H2O. So what will happen here? What do you get? You have to write the product. You can see there are 3 methyls, isn't it? So when I am removing H2O, I am keeping a double bond. So option A gives rise to the mesitylene, right? 1,3,5-trimethylbenzene is called commonly as mesitylene, and you know this reaction very popular, isn't it, right? You should know how to write the product. That's an art actually. So check out option B. So giving rise to what? 1,3,5. You have to establish a bond here, here and here, right? Got it. So option B is also giving rise to, you know, bromoform reaction, wherein what will happen that this whole group will be converted into, right? This whole group will be converted into COOH, no? Because iodoform test is like bromoform. This group goes leaving behind 3 moles of CHBr3. Along with that, you will be getting 3 COOH substituted at 135 positions. So this is just first product which is obtained. However, this when treated with the soda lime, you will be getting 3 CO2 loss to give you benzene but not mesitylene. So this cannot be the right answer. And this when treated with, anyways, we know that oxygen goes, the Clemmensen reduction. This is easier option. So option D is correct. So right answer for this question is A, B and D, isn't it? Very interesting, right? Just check out the next question. You can see that there is a series of reactions that are being done on the substance X, where you can see that there is a substance which is being taken, which is replacing the OH by, so all of them are having what? The OH groups. However, this reaction in polar aprotic solvent follows SN2 mechanism. This seems to be the Finkelstein reaction SN2 mechanism. Again, the azide substitution is also SN2, because here you can see that the solvent set that you have taken is polar aprotic. That's how I ascertain that the mechanisms are going to be what? SN2. You can see that we will go in reverse, right? You know, this is the reactant, this is the product. You know, you have to identify the reactant. So there are 2 times the inversion is taking place. One is 1 to 2 and then 2 to 3. Inversion. So alright, I hope you understood, isn't it? Now we can see that here, since I know the answer, I am directly writing the structure. Otherwise you have to carefully sort out. I will take this and I will carry out what you call the SN2 reaction by using PBr3. So what will happen? The inversion of configuration will take place where OH will lie opposite, isn't it? I mean, the OH is replaced by the bromine when you are treating it with. Now let's look at the next question, where X is subjected to the sequence of reaction. You can see that you got enantiomerically pure. That means 100% of only one substance is obtained. There is no enantiomeric mixture. That clearly indicates that this is predominantly SN2 mechanism. And also it is seen that the solvents which are being taken here are ether, acetone and dimethyl formamide, which is nothing but what? Polar aprotic. And you know, these polar aprotic solvents also support the reaction to take place via SN2 mechanism. And in SN2 mechanism, what will happen? From the starting compound, whatever is the starting compound, you know that inversion of the configuration is the concept, right? So you take a substance, alright, and carry out the inversion of the I will take this substance for the instance. You can see I am treating it with PBr3. Alright, so I will give you a retro method also. Since I know the answer, I am writing it like this. So you will be getting what? Bromine substituting the OH. Subsequently, the Finkelstein reaction is carried out. You know that you will be getting what? First, let me write the product. You got iodine in place of this thing, and then finally when this is treated with sodium azide, you know that this will come dotted. So how to solve this question? Because I know the answer, or I can comfortably write it this way, but when you are in my position, what you have to do is you have to go step by step in the backward direction. You can see that this is projected backward, right? The hashed line, right? You know, that means the previous substance, that means previous to that, that means iodine would have been at or towards the observer. Then again you go by one more step backward, that means bromine would have been away from the observer, isn't it? That means OH, you can see, go by one more step, OH could have been towards the observer, right? Isn't it? Alright, so you can see that you got X giving rise to Y, giving rise to Z, and finally giving rise to your ultimate product, say the product. And you can see in product, this is dotted, that means here it is thick, that means here it is dotted, that means here it is thick, and here it was OH, this became Br, this became I, and finally N3. So this is the retro method of solving the question. Hope you understood the method or technique, isn't it? Now let's see the next question. You can see that there are compounds on the list 1 and list 2 are the products, and in between the reagents, and you have to find out the proper matching to list 1 and list 2. Is a series of reactions that are taking place. You can see that compound, it may be a starting compound or intermediate, right? So you can see that 2 is first to be tested, like you have got the substance, this 2 is subjected to the OS analysis. So how you are going to do the OS analysis, you know. So what's happening here is that COOH, CHO, this is your first product of this reactant when subjected to the OS analysis under reductive medium. Now you see this is being treated with sodium borohydride. You know that sodium borohydride hardly reacts with the carboxylic group. It reacts, however, with the aldehyde group. So what you're going to get? You will be getting CH2OH, COOH. So what will happen in the next step? You are carrying out the dehydration by using a strong acid. So what will happen here? You need to eliminate H2O. Alright. When you eliminate H2O, you will be getting C double bond O CH2. So P and S are commonly given, P and S are commonly given, and however U is matching but not T. So right answer for this question should be option B, right? So option B is the right answer. I want you to check the rest of the options. Alright. Let's move on to the next question. What's that? You've got C6H10O. You need to find out the double bond index first. That is degree of unsaturation. 16 to 2 plus 2, that is 2 into number of carbons plus 2 minus hydrogens by 2. So 14 minus 10 by 2, that is double bond index is 2. And this clearly seen that this is reacting with a Grignard reagent, so it has a ring. That's how 1 degree of unsaturation is compensated, and also have a pi bond, right? Now this is treated with the Grignard reagent. You can see all the options are 6 members, so I could bluntly take the 6 membered substance, right? So you got CH3 and OH. So this is your Q. Now this is heated with what? This Q is heated with what? Concentrated HCl. So you know that it's not a dehydrating agent, it's only a substitution agent. So your S, the major product, will be OH replaced by Cl. So this is S. So do you see any S like this anywhere? You can see, isn't it? Now let's see the remaining reactions also. You got Q, and this is subjected to heating. You can see that we have used the acid and heating it so that dehydration can take place. So you will be getting what? The dehydration product. So this is R, isn't it? So you can see if there is any matching with R, but nothing is mentioned about R. So let's move on, isn't it? and this R is subjected to what? The anti-Marconi addition of the HBr. You know how the product would be written. So bromine comes here, isn't it? So you can see that CH3, and so C is perfectly matching. So this is nothing but your U. Alright. So if it is matching perfectly, that means well and good, right? So what about U? So U is not this, so option A is ruled out. Okay. What else we have? S is not this, so option B is ruled out. What about U and T? So you got U, isn't it? U is matching, and what about T? Huh? So you can see that in T you have got a reactant, that is T, which is substance is being taken. Let's see this option D also. Is it matching or not? So I'll take T and reduce it with hydrogen presence of nickel. I'm not sure about this, but once let's check. CH3, and then Br2 in presence of light gives rise to R. Did we get R so far? Yes, we got R, but you won't get R by this way, isn't it? So you won't get R by this way. So this is absolutely not matching. Okay. So if the reverse is done, I think the arrow should be, isn't it? The arrow should be on the other side, right? You know, there is a mistake in the question. In the arrow in the other side, you can see this is R, isn't it? Now this substance, this is actually the opposite. The question is wrongly framed here, or from the source from where I picked up. You can see R, and just check out R. Where is R? This one is R. You can see it is being reduced by hydrogen in presence of nickel to give you this product. Then this subsequently was brominated. You know that free radical substitution occurred at 3-degree position. So this is T is absolutely correct answer. So right matching to this question is option C and option D, isn't it? Move on, isn't it? You can see compound P and R upon ozonolysis produces Q and S. The beauty is that the molecular formula of both the compound is same. The molecular formula of Q and S are C8H8O. Q undergoes Cannizzaro reaction. That means it has no alpha hydrogen. Undergoes Cannizzaro but not haloform. That means it doesn't have COCH3 group. Meanwhile, S undergoes haloform. That means S has that group, COCH3 group, but does not. That means it has alpha hydrogen. There is no Cannizzaro reaction for S. Now, based on that, you have to predict the product after the ozonolysis, isn't it? Reductive ozonolysis. So, I am going to do the ozonolysis on all the substances. So, you can see that I will be getting the products accordingly. You know how to write the ozonolysis product, isn't it? This is the easiest way of writing the ozonolysis product. So you have to write the ozonolysis product. So what do you get in option A? From option A you got CH3. We are not doing it extensively that your benzene also get CHO plus C double bond of CH3. Okay. So you can see if I assume these two are P comma R. If I assume these are P comma R, the products that are obtained as what are they? Q comma S. The product obtained are Q comma, what is that? Yes. So P gives rise to this, isn't it? R gives rise to S. Q undergoes Cannizzaro reaction, right? Because it has no alpha hydrogen. So first condition is obliged, but not iodoform because there is no COCS3. Whereas S undergoes haloform because it has COCS3, but not Cannizzaro because this has alpha hydrogen. So A is matching to our requirement. Now let's write the product over here. You can see that there is this group CHO. This upon ozonolysis gives rise to this. What about B? Check out C double bond O CH3. So you can see that this also has the same arrangement like this. This gives rise to iodoform test. This gives rise to Cannizzaro. So this is also matching, isn't it? Let's see the next one. This is having alpha hydrogen atom. All right. And this is having C double bond or CH3. So this is also matching. You can see that, right? The ozonolysis product, this has alpha hydrogen atom, isn't it? And this has COCH3. That means iodoform test. Matching, isn't it? P and R is being asked. Conditions are obliged. This also has CHO and this also has COCH3. So all the options are perfectly matching to the question, isn't it? So you have to identify the P and R. So Q undergoes Cannizzaro, yes, but not haloform. If there is any chance that any of the option gives rise to haloform in the ozonolysis product of P, no. And is there any chance that it gives Cannizzaro? No, because COCH3 is common in all the product, isn't it? Yeah, ABCD is the right answer for this question. Look at the next question. In the reaction sequence, you have to identify the sp2, that means the pi bonded this thing. So you can see when you are doing the ozonolysis, you will be getting double bond O's. All right. So after getting the double bond O's, you have to write the concerned product here. After writing the double bond O's, you know how to write the oxime from the hydroxylamine addition, right? Simple property of the aldehydes and ketones that they will be added to the nitrogenated nucleophiles to lose water, isn't it? So NH2OH. So what will happen here? Double bond NOH, double bond NOH, and you are writing here another double bond NOH. So you can see the total number of unsaturated, 1, 2 in every case, right? So unsaturated carbon atoms are 4 and nitrogen atoms are also 4. So right answer for this question is 8, isn't it? All right. Next question. Yeah, there ends this slide. So we have covered almost all the questions, right? So keep watching the videos. I'm sure that you are liking them. So press the like button, share and subscribe to the YouTube channel. Thank you for watching. That's it for today.